This question states if the absolute value of the ultimate compressive strength equals 150 megapascals and the ultimate value for the tensile strength equals 100 megapascals, will a brittle material under the depicted state of stress fail according to the Mohr criterion? So let's go ahead and approach this problem by thinking about what the Mohr criterion looks like on a sigma 1, sigma 2 plot. And then we'll go ahead and figure out the state of stress. And then we'll go back to the sigma 1, sigma 2 plot and figure out whether or not failure might be occurring. So as a recollection, the Mohr criterion compensates for the fact that and I'm already drawing this incorrectly. It compensates for the fact that the compressive strength for brittle materials is often greater than, or the absolute value of it, the magnitude of it is often greater than the ultimate tensile strength for brittle materials. And so for the drawing of a sigma 1, sigma 2 plot, what we do is we put one corner, whoops, where did it go? There it is, okay, where we have essentially sigma ultimate t, that's in tension, and sigma ultimate t there, and then we draw a little box in quadrant 1 that looks kind of like that. And then we come down to the other side to quadrant 3 and we draw a dot for the compressive strength, the ultimate compressive strength of the material. And it has a larger magnitude, 150 megapascals in this case versus 100, so it's down a little bit further. And this really should be a box that's square-ish. You can see it's not super square-ish there, but you get the idea. And then the Mohr criterion, and we talked a little bit about how you have like multiple Mohr circles potentially on the uh, sigma tau axes, but the Mohr criterion suggests that you have kind of this curvy space or these curves, okay, that go from this sigma ultimate c comma 0 to the 0 comma sigma ultimate t, and you have the same thing happening on this end. And then we go further and we say, all right, there's going to be a linear approximation that we can make for that curve, and we need to make sure that our operating point is in the envelope if we do not want to have failure. Notice this plot is a sigma 1, sigma 2 plot, which means we have to get an equivalent state of principal stresses in order to make this comparison. So now we go to the described state of stress where we have 90 megapascals and we'll call it the x direction, and 30 megapascals in the tau xy, or for tau xy. So what are we going to do? We're going to draw a Mohr circle for this state of stress, figure out what the principal stresses are, and then make a comparison on the sigma 1, sigma 2 plot for the Mohr criterion. So we'll say, all right, sigma x, I don't know, we can change colors, why not? Sigma x equals 90 megapascals, and tau xy equals 30 megapascals. What we've done here, right, is said that this is the x direction and this is the y direction. We notice that we are having these arrows meet up on the right side, or the upper right, and that signifies, at least with an x and a y, as we've got here, that tau xy will be positive 30 megapascals. So for our Mohr circle, we can go ahead and figure out what sigma average is. And that is going to be just sigma x divided by 2. So that's going to be 45 megapascals. And we can draw our sigma tau axes, putting, let's say this is the sigma average, like that. And then we'll come out over here. They're both positive. When I say both, I mean sigma x and tau xy are both positive. So this will be what we have for our sigma x, and our tau xy will come down, let's say, to about here, right? So, whoops, it didn't stick. Still not sticking. There we go. And we have our tau xy like that. So this point right here, that is sigma x tau xy. This point is sigma average comma 0, and this line that we draw, that is the radius. Okay? So we see that Mohr circle is going to take us a little bit past here, and it's going to take us a little bit over here, and so we'll try to nicely draw a circle, okay, like that. And we need to figure out what the principal stresses are. So we're looking for, that's messy, sigma 1 over here and sigma 2 over there. And this is a 2D state of we're given a 2D state of stress, which means that we can go ahead and assume that the stress components in the other, or in sigma 3, I guess you could say 0, and that tau yz and tau xz are also equal to 0. So our sigma 3 is going to be at the origin. So that's all nice and good. We need to get the sigma 1 and the sigma 2, so then we can plot them on the Mohr circle. And we can already see that sigma 1 is going to be positive, sigma 2 is going to be negative, and so that puts us in quadrant 4. So we're going to be in this quadrant once we figure out what those values are. So how do we figure out what those values are? Well, we got to figure out the radiuses, and then we can say the radius plus the sigma average will give us sigma 1, and sigma average minus the radius will give us sigma 2. So let's go forth and try this. So the r is going to be what? The square root of this sigma x minus sigma average. All right, so sigma x minus sigma average is going to be the 45 megapascals. So we have 45 squared, and the so that's this distance right here, right? And so that's well, depending on how you're looking at, it could be the adjacent, and the opposite is going to be tau xy. So tau xy was 30. Had all this space that I just messed up its proper. Like this. Okay? So you can plug this into your calculator and you will get 54 megapascals. And now we want to calculate what the sigma 1 and the sigma 2 are. So sigma 1, I don't know, should I change colors? Why not? Sure. Sigma 1 is going to be the sigma average plus R, which is 45 megapascals plus 54, so that gives us 99 megapascals. And sigma 2 is going to be sigma average minus R, which gives us about minus 9. 45 minus 54, that would be negative 9 megapascals. So those are the 2 points, sigma 1 and sigma 2, and now we come over and we need to figure out where they are relative to this line, okay? Because if we're in the envelope, then we do not fail, but if we're outside the envelope, then we will have failure. And so this is, maybe not exactly to scale, but let's take a look a little bit. We see that the sigma ultimate is 100 megapascals. Okay, so this value right here is 100, comma 0, right at this point. And maybe I'll change the color back over here. And so we are pretty close to that at 99, and so we're like right up next to it. And so I don't know if I'm above or below. So how do I figure out if I'm above or below that line? Well, as we discussed in class, we can figure out the equation for this line. And to do that, maybe it's helpful also to write out what this coordinate is. This coordinate is 0, comma, ultimate or sigma ultimate c. Here, it is the sigma ultimate c, and that is 150 megapascals. You see up here, that's 150 megapascals. So we're just going to say this is minus 150 megapascals. So what does the line look like? Well, it's going to be sigma 2. That's because that's the y in the y direction, right? So we're trying to do mx plus b essentially, right? And what's the slope? Well, the slope, we know the rise is 100 megapascals. So I don't know. I guess I'll just write it out generally first. Ultimate tensile strength. And the run, oh, I'm sorry. That's not correct, right? The rise, because it goes from minus 150 to 0. So the rise is going to be the absolute value of the ultimate compressive strength. Apologies. And the run is going to be 100 megapascals. So that's going to be the sigma ultimate tension times the sigma 1, that's essentially the x, right, parameter. And then we have a y-intercept, and that's at minus 150 megapascals. So that actually ends up being plus sigma ultimate c. So the line that we get is going to be 150 megapascals, and you just forgive me, I'm going to say that the units cancel out, times or divided by the sigma ultimate tension, so 100 sigma 1, and then this ultimate tensile, that means minus 150 megapascals. Okay, so that's the line, and this is essentially just 3/2 sigma 1 minus 150 megapascals. So let's figure out where the point on the line is. Okay, so on the line, okay, that point there, right, that would be on our curve, and we know that we're interested in 99 megapascals, comma, what? Well, let's plug in 99. So if we plug in 99, okay, we are going to get something. Actually, what are we going to get? Let's see, 3/2. It comes out to be about this. This is going to come out to be. So if you plug it in, I have the number here. So I'll just say that's minus 1.5 megapascals. So 3/2 times 99, okay, is pretty close to 150, but it's just a little bit less than 150. So I guess based on what this is 148.5. So we'll just say that 148.5 megapascals minus 150 megapascals. Okay, and so that's going to give us minus 1.5 megapascals. Okay, so that's where we are on the line. Well, what is the actual coordinate for our operating? It's minus 9. So our operating, maybe I'm exaggerating that a little bit, all right? But our operating, okay, so we'll just call this uh, sigma op, comma, tau op, okay? Or sorry, sigma 1, of course, comma, sigma 2 op, right? And that has the values that we discussed here. And so it is outside of the box, all right? So we can say that sigma 2 op equal to minus 9 megapascals is less, okay, it's outside of the minus 1.5 megapascals. So we could see that's going to be maybe sigma 2 line, we'll call it, which was the minus 1.5 megapascals, just like that. So we predict failure according to the Mohr criterion for brittle materials. All right. I hope you have found this example useful. And to recap, what we've done is we've gone from a description of the ultimate compressive strength and ultimate tensile strength to Mohr's criterion, to looking at the operating state of stress and getting the principal stresses so that we can then make a comparison to the Mohr criterion. But in order to do that, we also have to figure out where we are relative to one of the outer boundaries of the Mohr criterion envelope. And then we're able to make a comparison, or once we know if we're in or out of the envelope, then we can say whether or not we failed. All right. Thank you again.